Okay, so I would like to start with the projects. Okay, the projects. I suppose many of you already read the description at least, right? To get some vague idea. Okay, let me just talk about it. Because I think the most challenging part in the beginning will be the verification tool you're going to choose. I'll give you some general guidance today, so you will hopefully you wouldn't have trouble. Okay. The problem here, let me talk about very quickly. So this diagram is just like an extension to the diagram we introduced in the first lecture. Okay. So basically, let me talk about each component, and you will have an idea what you have to do. So that's why I said maybe you're not really recommended to do everything in a single member. That's not so doable, I would say. Maybe 2 or 3 will be fine. First of all, you will have to design the syntax. Is completely your freedom to design the syntax for a programming language. So I would say programming. And for this one here, I would say your team member can brainstorm about what features you want to support. Maybe your favorite language is maybe Python. You want to support a certain feature over there. And maybe your favorite language is iPhone. And then you want to put some features there. I don't know. Maybe, right? So it's completely up to you. If you like C++, you can also put features there. However, I want to warn you something, okay? As I mentioned in the instruction, I want to emphasize right in the beginning. You may not want to try to design this part right away. It really depends on the tool that you choose. Not necessarily everything you want to support can be so easily translatable into the verification language. Let me mention that, okay? So I would say here, you can brainstorm some list, but eventually whatever that's feasible depends on the tool you choose. So I want to talk about the tool in general in just a moment, okay? And then your compiler over here, of course, you're required to use ANTLR 4. And hopefully many of you maybe at least started to look at the tutorial series. That's why I want to make assignment 3 very related to ANTLR 4. So I'll try to make it light for assignment 3 and 4, but you should do something to get yourself familiar with ANTLR 4. Tutorial video, pretty long, about 5 hours, so plan your time, okay? I wanted to give you all the detail you should know, at least to get started, so you wouldn't get stuck at this point. For ANTLR 4, I'll talk a little bit about the design for your compiler in just a moment, okay? Just give you a quick heads up. And then eventually, at the end of the day, this is really what really matters when we evaluate. Whatever it generates over here will be, we call it output, but at the same time, it will be the input of some verification tool. So I gave you a list of tools which I'm going to talk about. Once I give you some brief introduction today, you're expected to do a little bit of research for 1 or 2 days to understand a little bit more. Okay, I'll give you some idea. You can feel free to ask me questions. Okay, whatever you choose over here, so the output here should be considered as type correct and also syntax correct by the verification tool. So that means when you try to program your compiler for transformation, you got to be very careful. You want to do testing right away. Okay? At the end of the day, we have certain list of basic features I think you should really at least support, like a variable declaration, variable assignments, etc. If you can get at least those done, you will receive a passing grade, at least. But I don't think that one will be too difficult, given that you got 6 weeks. For those of you who are more ambitious, try to support as many more as you like to impress us, and then we'll give you a higher grade. Okay, that's kind of the rule. So far, any questions? So far, just overall picture. Okay, hopefully that's clear to you. Okay, verification tool is really important. So these are the milestones. Let me talk about the milestone. I try to give you 2 intermediate deadlines before the final project, rather than saying I'll give you 6 weeks and do whatever you can. But I want you to have some intermediate checkpoints. So these are really meant to help you. So better make sure you get ready before you have a meeting with me, right? Let's save everybody's time. Okay, I would say number 1, you really want to sort it out after the class today. You want to find your team members, okay? And then you want to start looking for what should be the target verification tool you want to use, okay? And then you'll be next Tuesday, March 3rd. You want to submit this particular file. I got a format in the instruction, okay? Submit this file, so me and the TA, we can make a record, okay? Do this one, okay? And then the first checkpoint for you is about 2 weeks from today, okay? What I really want you to do is I'm going to send you some Doodle survey to see what time that will actually work for both me and your team. So either Thursday or Friday, I'll give you the list of times. About 2 weeks from now until March 5th or 6th, your first priority is, number 1, commit to the tool you want to use for verification. Number two, study as many examples as you can to understand how it works. Because once you understand how the verification tool works, you will have much better idea how you program the transformation. Okay? To make it clear. And of course, this verification tool might be new idea to every one of you, but that's just a reality. When you try to build a compiler, the target language may just be something you are totally unfamiliar with. Okay? But you're going to do a little bit of learning here. So that's why I just make it 3%, very light. As long as you can demonstrate that you really try to understand, at least one team member can understand how things work, then I'll be happy. Okay? That's a minimum requirements. Okay? And then another 2 weeks passed, about 4 weeks after the project is released. Let's do another checkpoint, March 19th or 20th. What I want you to do is this. So basically, within 4 weeks, I want you to at least make a working compiler for the basic features. So rather than saying you try to design a whole syntax for the first 4 weeks, and then try to do maybe the implementation for the next 10 days, you only leave 1 day for the testing. That's not the way to go. Okay? What I want you to do is I want you to make just a whole workflow for your compiler, everything from the beginning until the end, just work. Number one, you want to make sure it works for variable declaration in some form of your syntax, for assignments, and also for referring to variable and everything here. There's no loops over here. And the reason that I put specification over here is because in order to verify your source program, you need to have some form of specification, such as precondition, postcondition. So in your program, it should not be too surprising. You have to somehow support the specification of precondition, postcondition, and etc. Okay, I'll talk a little bit more about it. Okay, and exactly what you should support depends on the verification tool you choose. Again, everything depends on that. Okay, and then what you have to do for the second checkpoint is easy. You basically just show me how your compiler works. I want to see some working compiler. I want to see also 5 different example of your running your compiler using all the basic feature. So I hope that's reasonable. So within a month, I want a working compiler just for the basic features. Okay? If you pass this second milestone, you're guaranteed to pass, at least for the projects. But of course, hopefully, within another 2 weeks before the due date, you can do more. And then the more you can do, the higher grade you will get. Okay? Okay. Any clarification you need at this point? Okay. Yes. Oh, you need the examples over here? Basically, this example here should be, for example, you can do a bank example. And the bank example over there is going to be written in terms of the syntax you have designed. And then the example is going to make use of, basically show off what you have done so far. Maybe you show how I can declare an array of accounts, how I can refer to, how I can change the value of the accounts, things like that. Okay? But what example you want to make, I'll leave it to you. But if you want to have my advice, you can speak to me offline. That's fine too. Okay? I want to see something not so trivial, right? For example, don't just give me a program that's only doing a swap of 2 variables, right? That's not so, maybe it can be one of the examples, but you want to show me something that's more sophisticated. Okay? Okay, and then finally, your project is going to be due April 6th. So you got 6 weeks. Again, it's a challenging problem we are doing for this project here, but I hope you will gain some valuable experience here. You can definitely put on your CV, you have done some program, some compiler for program verification. I think that's quite nice, maybe for your future employer to know. Okay, so now I would like to talk about verification tool. I think that's the most important bit because that's something completely new to you. Let me just go through the list and mention a little bit, and then I do have some background to mention to you. I want to make it as clear as possible. Of course, you got to do some further research. Again, you got to use ANTLR 4. And then I got 1, 2, 3, 4, 5, 6, and 7 tools for you. But after the guidance today, if you feel like you want to find another verification tool of similar kind, feel free, but confirm with me. Okay? Okay. So now so all these tools can be divided into 3 different categories. Okay? I'm going to talk about each category first, just give you some example to get an idea. Basically, there are 3 paradigms we're talking about. One is called model checking. Okay? Second paradigm is called theorem proving. And the third paradigm is called constraint solving. So each of the tools can be fit into exactly one category. Okay, so let's talk about model checking. Okay, any one of you heard about this term before, model checking? Okay, yeah, good. If not, that's fine. I didn't assume anything. Okay, let's talk about model checking first of all. Model checking, for example, out of these tools, PAT and also SPIN. So these are the model checkers, and also Alloy. I'll be here. So Alloy, also SPIN, and also PAT. So these three tools are more into the model checking paradigm. Okay. So let me just talk about general sense about how model checking is going to be done. Okay. Number one, a transition graph is going to be built based on the input program. So like a DFA. So you will hope the number of states will just be finite, so you can actually do some checking. Okay, I will use one example to explain to you. But number one, there will be some under the hood transition graph, and then there will be some model checking algorithm, basically some graph traversal algorithm, maybe extension to that first search. That will simply just go over the transition graph and try to see if, for example, every state satisfies certain invariant property. I'll give you one example in just a moment. Just get the principle straight. So some algorithm, in which case you don't have to worry about whatever verification tool you choose, they got it implemented already. And then you're going to verify certain property. So now, for any tool you might choose, you want to see what kind of property they can verify typically. So you can reverse engineer to see what your syntax should support. Okay? And then the greatest advantage about model checking is it's a completely automated process, meaning that if I supply input to the model checker and the input is considered as syntax correct and type correct, you just click on one button and then they will tell you in principle either yes or no. Yes, the property is satisfied for every state, or no, there's at least one counterexample in certain states that's not satisfied, either yes or no. However, there's a third possibility. Okay? What I will put here is think about you have some input into the verification tool, the model checker. So that's the model checker over here. And you might either say, yes, the property you try to verify is simply true. It's going to be satisfied. You might say no, in which case they will give you a counterexample. And I can also give one example in just a moment. And then there's another possibility. It's like not terminating. So this is inherent limitation for the model checking approach, because transition graph really depends on the performance of your algorithm, really depends on the size of the transition graph. If your transition graph is very large, it takes forever to really run. Well, when I say forever, depending on how many resources you have for your computer. Okay? So this is so-called state explosion problem. So this is a very well-known term in the research field, state explosion. So it simply means if you try to take the combinatorial values of all the input variable together, for example, if you got integer I here, and also integer j, and that's 2 to the 32, right? Possibility. Another 2 to the 32. If you want to combine all the possible possibilities, multiply them. That's a combinatorial explosion. So typically for the model checker you're using, they will have a way to restrict the input domain size you have to consider. So that will affect your design for the input language. So if you really choose model checking, which I'll be quite happy about, and you got to watch for that, state explosion. And for your information, Alloy is developed by MIT. So it's quite a well-known tool. And SPIN is used by NASA. And PAT is actually developed by some very well-known research university in Singapore. It's also very popular among the field. So I would say if you try either one of them, that's also a nice experience for you. Okay, let's just do one example to give you an idea. Let's say over here we have let's say we have a system, and the system simply got either increments or decrements. Very simple. Okay, and then let's say we only have one variable called x, integer. Okay, I declare x to be integer. Potentially, what would be the size of the state graph? You might think should be 2 to the 32, right? Because integer is 2 to the 32 possible value, but not the case, not quite. If you're smart enough to specify your input program, you can restrict quite a bit. In this case, for example, I'm just using the syntax hopefully you know about. So require here simply means precondition. Whenever you're trying to increment, you're assuming that the value for my current x is simply strictly less than 5, up to 4, basically. And then if you try to do decrements, it should be larger than or equal to 0. So that effectively restrict the input domain, which will be from 0 up to 4. Only 5 states is needed. Okay, let me give you a little bit better idea. What the model checking algorithm will do is to first of all build a transition graph. Let's say initial value for x will just be 0, let's say. And then they will try to see for every state, I will try to call increments and see what the resulting state is. I'll try to call decrements and see what the resulting state is. I will only build the next states if the precondition is satisfied. For example, in the case where it is 0, can I build the next state for increments? Yes, indeed. So I can simply say increments that will lead me to 1. And now can I build the next states for decrements? Yeah. It is fine, right? Okay. So now if I do that, that will actually decrement this into -1. Okay, so far so good? Okay, that's the first step for the first iteration for the building algorithm. Again, it's implemented for you. I just want to tell you conceptually. And then you're going to branch out for every next state. Now, for this particular state, can we do, For this particular state, can I do increments? This one, sorry, this one. Indeed, because -1 is less than 5, right? So if I do it, I'm just going back. Increments. Can I do decrements? No, because -1 larger than or equal to 0 is simply false. So that's where I stop for decrements, right? So now if you keep going, basically what you will get is like this. Increments, decrements, and also increments, decrements, I'll just be complete. And also increments, decrements. Should I do one more? Maybe, right? It's up to 4. And also increments, and also decrements. That's the complete state transition graph. Okay, any questions so far? I hope you got enough intuition. So now, Raymond.
So if you didn't have those requirements, the transition graph would be infinite?
Very good question. So let's say this. Hypothetically, let's say, of course, if your input program should definitely support this, right? To support a way to have require over here. However, you cannot control what the user might do. That's beyond your control. If the user simply say, they don't put any require here, it's as if it's simply true. In that case, if you try to load this particular system into your model checker, as soon as you hit the button, it's going to get very, very, very busy. And then you will never, never end because transition graph takes forever to build. You see what I mean? Yeah. So now, I would say, in case you want to choose the model checking approach, I have some general advice for you. Okay? If you choose that, for sure, you have to support certain like a assumption or like a contract, I'll just say. You have to support certain contracts to make sure the input size can be restricted. Okay, and number 2, you have to support what kind of property you can verify. I'll give you one example. Let's say given this particular system, I can say, let's say if I support assert. Okay, I assert invariance, let's say that's also a keyword. Let's say x larger than or equal to 0. So what this really means is, well, back in 3311, what does it really mean to be invariance? For example, class invariant means every object should satisfy that condition, right? If you say the system has this invariant x larger than or equal to 0, that means every possible state should have this property satisfied. Is it the case? No, apparently not, right? Because you can see -1. So in this case, what the model checker will do is to give you no, and what's more, it's going to give you so-called a trace to say, initialize your states, and then if you do a decrements, now this will lead you to a state which is -1, and that one will violate this invariant property. So that's so-called counter trace. I'll write it down. And then I'll take your question. Yes? Oh, I just say, let's say there's an initializer there. I just didn't put it. Let's say it starts from 0. I would say it's completely up to you. You can say maybe you can let the user specify, or maybe when there's no explicit initial value, you can do a type checking and then report back to the user, you didn't initialize your state value. Right? That's again completely up to you. Okay? Guys, any question about model checking in general? I just want to give you some intuition. Okay? Basically, you have to make sure the contract or contract you support in your language is sufficient enough to give to let the model checker restrict the input domain. But what's the best way to know how you can restrict it? Study the model checker. So they will actually give you some hints. Okay. One more thing I want to say. When you study the example for model checking, they basically got things like LTL or CTL. I'm pretty sure you'll encounter these two keywords. Okay. One is called linear temporal logic, and this one is maybe called computational time logic. Okay. These are quite advanced math over there. I would say if you really choose to do model checker and then you encounter these terms, you need advice, come to speak to me. That'll take a little bit of explanation. In your final products, I wouldn't expect you to actually do the full support for these. That'll be a little bit too complicated. Okay? But anyway, if you really choose to do model checking tool, I'll give you some special advice during our meeting. Okay? Any question in general for model checking? Okay? Interesting idea, actually. Very. You know what? Model checker was initially done by a well-known researcher in Carnegie Mellon University in the States. By using the model checker about 20 years ago, they found a very rare case for the Intel Pentium processor. There's something like that. Anyway, so that's how they found it. So model checking tool is really used in the industry. So if you really use it for your compiler, I think quite a nice claim to on your CV. And as far as I know, I read some paper previous for Alloy. This is a more lightweight model checking tool. They actually use this to find a secure flaw in the Android app system. Interesting. Anyway, so model checking tool is really interesting. The best thing is it's automated. The worst, what you really gotta watch for is a state explosion. Okay. Okay, let's talk about second paradigm. Second paradigm is called theorem proving. Okay. In some way, this is something you have done for many years already so far. You just didn't realize it. In some way, theorem proving is more like the final part of 3311 about Hoare triple. If that rings the bell somehow, right? At least you remember the name, right? Hoare triple plus 1090. That's what theorem proving is. Okay? Let me give you some idea. For the theorem proving, basically you do things completely differently. There's no transition diagrams whatsoever. Okay? And then what you do is somehow the system or your source code will be encoded as predicates. I'll talk about encoding in just a moment. Okay? Will be encoded as predicates. And actually, let me talk about 3311 a little bit in case you want to go for this path. Okay. Let me impress me. Okay. Well, you kind of remember this, right? Maybe. Okay. Let's say this is a swap program. Okay. Swap program. We got precondition, we got postcondition, and these are the specification of your routine or your method, right, or feature. And this part here is the implementation, right? So now, as far as you can recall, how do we prove that this particular feature, given its implementation and specification, is correct? How do we do it? Sure, Hoare triple, but can you be a little bit more detailed? That's why I just mentioned that, right? If you can give me just a little bit more details, that'll be useful for everybody. I rely on you.
The idea is you want to start the precondition being true and then running the code you can satisfy.
It's getting there, but not quite exactly, but that's okay. I wouldn't blame you. It was back in 2017, right? Basically, the idea would be, do you remember WP? Yeah, that's good. Basically, if this is S, the implementation here, S, and then this is a property we want to establish, and given y larger than x, we can calculate that, and then whatever precondition here should entail this particular WP, right? That's what you learned in 3311. In some way, we're encoding your program as predicates. You can think about, I'm pretty sure I mentioned the word encoding when I was teaching this in 3311, but I wouldn't expect you to appreciate what encoding really means, but now you will see why. Let me say again why it's called encoding. Think about this is your source, which is just a normal program with implementation, with loops maybe, in which case you got variant and invariants. And in order to verify that using a theorem proving approach, you have to, one way to do it is to encode it using the WP, which is itself a predicate. And then make sure the precondition there is no weaker than the weakest precondition, right? That's why we had to prove this particular implication. Okay, that's one way of encoding. And then the second part here is the challenging bit for the theorem proving. The way to make theorem proving work is you have to somehow conduct a proof. Remember in 1090, in the exam, I'm pretty sure you're given some very hard problem to prove, right? How do you prove it? You got to think about, yeah, you want to say something? Yes.
I mean, like, we have a list of axioms that,
Exactly, you got axioms, okay? So that's a particular proof system, let's say in your 1090, you definitely got some axioms which you don't have to prove, just assume them to be true. And then you can also prove some additional lemma, like helper theorems. And then in order to prove this particular theorem, you use them to actually deduce. Okay, one example for you, I'm not going to prove it, right? Let's say, given these two things as axioms, how do you prove this is a theorem? Right? Okay, hopefully you can do it. If you cannot, speak to me, right? That maybe some lack of background you need to, oh, actually, yeah. How about this? This guy is equivalent to by the definition of implies, which is over here, right? In that case, I can say, well, actually, just go with the equivalent proof, right? In case you got trouble, let me know. I'm just give you the idea. And the biggest disadvantage for theorem proving approach is you got to conduct the proof yourself as a user. So it will be a manual process. So if you do choose this particular tool for your projects, that means, let me go back to the diagram. Okay, let me be precise. If you did choose the theorem proving approach, let's say if this happened to be a theorem prover, for example, coq. Okay, that's one of the theorem provers. If you choose a theorem prover, that means your program should really generate something, your compiler should generate something that's readable by this particular theorem prover. And then you expect the user to actually do some proof. And how to do the proof is beyond your control. You don't have to worry. However, if you choose this one here, you have to somehow justify, just informally, you don't need to prove anything. Justify informally why you believe the way you encode is correct. You got to convince me in the TA, okay? But we'll speak more about this. And for the theorem proving approach, basically, what are the examples? You have basically PBS. So this is actually used in the 4312, the software engineering requirements course. However, to be honest with you, I wouldn't recommend this. But the reason I included this is because it's a good tool. It's used by, oh, by the way, it's also used by NASA. It's also used by them. However, the interface takes quite a bit of learning curve. Yeah, they use Emacs. You know, I know nothing about Emacs, to be honest. I used to work with PVS when I was doing my postdoc for 3 years, but even until now, after 3, I forgot all the details. But you know, that shouldn't stop you. I'll be very impressed if you choose PVS. Very impressed. I tell you what the biggest advantage is. If you choose PVS, they got lots of learning resources on that particular course website. Okay? If you want to speak to Jonathan about the PVS, I'm pretty sure he'll be willing to speak to you about the instructor. But you know, that's another story, right? Okay, PVS is one. There's another one called coq. This one I don't know much, but it's quite a recent theorem proving tool that's very popular. That one they seem to get the most user-friendly interface. Okay, I'll just mention that most user-friendly interface. Isabel, I will personally be very interested if you choose that one. That one is a theorem prover developed by the Cambridge University, not Ontario, actually, of course, UK, right? So, and that one is also another theorem prover. Okay, you can choose either one. If you want to find another, well, if you really should you choose this one here, there's something called Rodin. I'm pretty sure you know about it. Yeah. Anyway, Rodin is also used in one of the software engineering courses in the 3rd year. But if you want to use it, that's fine too. But you're gonna consult with me first. Okay. Okay. So far we cover theorem proving. We cover about and there wouldn't be any state explosion problem. So whenever you want to say, you want to really do the theorem proving, you rely on deductions. You want to really use the relevant theorems to actually go with the deduction. So you don't have to worry about state explosion. Let me finish this and I'll get to you. So that's why the last point is really about complete input domain can be encoded. So let's say you simply got increments over here. Let's say use the same example. And then you simply say x is assigned to x plus 1. In this case, you don't have to worry about there's no such, it's actually infinite states. You don't have to worry about because you can use deduction using axiom or theorems. Okay? That's the advantage, but it's manual. Question?
I was going to say, when you say manual steps, like
Oh, when I say manual, I don't have a demo. I can do some demo later. What I said manual was, yes. Okay. To be more precise. Okay. How about this? For you guys, everything up to here, right, should be completely automated, right? That's your compiler's job. Once your compiler generate, let's say for theorem proof, let's say for PVS or COC, whatever output that's reproduced, the user of your tool have to manually load it into PVS or into the theorem prover. And then to prove it, they have to interact with the theorem prover and then try to do the deduction. But that's beyond the scope of your projects.
I understand that, but I mean that when we're testing ourselves, they interact with the one with the theorem prover that you said. Does that go along the lines of it just tries things on its own, or is it like that?
Good question. I think for the theorem prover, I think for all the kinds I mentioned, right, or for any kind you want to do, basically they do support some default, like a try. It may not be called try. For PVS, it's something called grind. Okay. Basically, what that means is, why don't I just try to let the theorem prover to try to prove it for me? For simple stuff, it can be discharged automatically. However, in general, if you got some very complicated theorem to be discharged, you would say, I cannot do it. In that case, you have to interact with the theorem prover to say, how about adding this particular assumption? How about go this particular path for the proof? Okay? Make sense to you? Okay, good. Proving itself is an undecidable process. It may be automated for certain cases if you guess the wrong path, if you guess the right path, but it may not be in general. Okay, that's about theorem proving. Okay, the easiest one is something called constraint solver. Okay, constraint solving here. Any one of you heard about something called Z3 before? Any one of you? You heard about it? Oh, why?
For Microsoft.
But how
I've used it before.
you used it before? For which course?
Not your course, because now.
Oh, really? Okay. Okay, let's talk about constraint solving. Okay, I have a mental challenge for you also at the end. Also, let's do some exercise together, okay? I'll be equally happy if you choose constraint solving, okay? Let's talk about the idea. Constraint solving goes like this. Again, your system, similar to the theorem proving approach, you're gonna encode your system as predicates, like whole triple, okay? But now, the way it works is the opposite. Rather than trying to prove something, they will try to find some witness that will satisfy the predicates. What do I mean? Let's say, for example, if I got this particular predicate over here, P and Q is equivalent to Q and P, right? If I simply fit this into Z3, that's a constraint solver. What Z3 will do is go back here to say, there is a witness, and they also call it model. In which case, when P is equal to true, and also when Q is equal to true. They just give you one example where this particular equivalence can hold. That's all they do. That's why it's called constraint solver. They try to solve the constraint by giving you one witness. Otherwise, they tell you there's no such witness. That's how it works in general. Is it okay so far? Again, how long it will take to solve depends on how large, how complicated the predicate is. In general, combinatorial explosion, as I said in the last point, can also impact the performance. That's an inheritance.
Like the problem beginning out if there's assignment linked to the true is actually incomplete.
Yeah, even the satisfaction problem. Yeah, but of course now when you talk about integer or even real number, they also support real number. In that case, that can be even harder. But I think for the kind of examples we expect you to develop for your compiler, I don't think you will run into this problem. I don't think. Okay. Now I have a mental challenge for you. Okay. As I said before, if I give this particular predicates into Z3, what they will give to me is like a binding to say when P is true, when Q is true, this particular predicate will be satisfied. But that's not what I want. What I really want to say is I want to prove that this is a tautology. A tautology means for any combination of P and Q, this will be satisfiable. Aha, you guys are pretty smart, right? That's good. Guys, for those of you who haven't got it, that's okay. I'm going to explain to you in case you choose Z3. Okay? The way this do is you got to do a little bit logical trick in the middle. Let's say this is my constraint solver, okay? Constraint solver over here. And then I simply give the, okay, let's say this. Let me just move it a little bit, okay? This is my constraint solver. And this is my input P, okay? I want to prove whether P is a tautology or not. What I should do is, my compiler, or your compiler, should, first of all, negates whatever predicate you want to prove as a tautology, and then pass not P to CS. So now a question for you. What if the constraint solver tell you, yes, it is satisfiable, versus when it says no, it is not satisfiable? Which answer is going to be telling you the original P is actually a tautology? Yes or no? No, good. The no option here simply means no violation can be found. Okay, no witness. No witness for the negation of P. That means P must be true in all cases. Okay, that's the only logical trick you got to do conceptually. Of course, there might be more things you got to worry about. Okay, so now I already talked about all the three paradigms. So I think with this kind of like a general insight, well, not insight, the general introduction to all these. So when your team members actually do the research, you hopefully be more guided. Any question about any of the paradigms?
I agree with that's only one tool.
I would say, yeah, choose only one verification tool for compiler. You don't need to do two. Okay. Yeah. Okay. I'll be very happy if it turns out each team is choosing a different verification tool. I'll be very happy. It will be the worst case if everybody chooses the same tool. But I shouldn't say worst case, but less prefer. Less prefer.
Well, there's like 8 tools, like 9 tools, and there's like 8 tools. So
I know, yeah, but of course you're also welcome to actually do a bit of research. If you tell me, for example, some tool you really need to try out, consult with me, and then I will just give you permission if necessary, okay, if possible. Yeah. Okay, if no question over here, what I would like to do is, let me say a little bit more about the project here, okay? So guys, I think what your team should do, maybe I think you still have a little bit of time in the beginning to spare. Maybe, assuming that you got 3 members in the team, right? Why don't you guys maybe to say each member is going to explore one particular paradigm to see how the tool looks like, and then meet up maybe in about 4 or 5 days, and then decide together which one you want to choose. Okay? Any question you have, you can let me know. Okay. All right. Hopefully that helps. And again, think about the timeline for this particular project, right? If you think about it, so this is today, right? After 2 weeks, that's the first milestone. That one there, you should really show examples of the verification tool. And you want to show me how to run it, right? I'm not going to give you any hints on running the tool, so you're going to show me, so I'm going to ask you questions as well during the session. So I really want to give you a little pressure, okay? Make sure, I would say this is the most important milestone, even though it's only 3%. Not very heavy, but I think it's the most important stage for your projects. And then after another 2 weeks, basically, you're going to show me a working compiler for all the basic feature. And notice that I'm not saying that you cannot start implementing your compiler from here. I'm not saying that, right? You can definitely start implementing your working compiler as soon as you think your team is ready, right? So this checkpoint is the latest point you should get it ready, I should say, okay? And then after another 2 weeks, you can try to maybe fix any issues or incorporate any feedback I might give to you in the meeting, and then that'll be the project when the project is due, and adding more features, okay? Okay. That's about the project requirement I'd like to talk about. And then at the end of the day, you have to submit basically the software package, so the TA and I, we can try that out. And also, you're going to write a user manual, okay? And then I'll be precise about what should be there about 1 month before the due date. Okay, I'll make it available to you, so you got enough time to write it. Okay? Any question about the projects in general? Okay? Okay, hopefully you can just meet a milestone. It's really meant to help you. So it's going to be something substantial, but I think you can still really achieve something at the end after 6 weeks. Let's see. Okay. Let's now talk about a little bit about the ANTLR 4. Very quickly, I just want to show you a few diagrams to emphasize to you. For those of you who already watched the video, any one of you finished the video already? Wow, good for you. Did you put it into triple speed or double speed? 1.75. Okay, sure. I thought already spoke quite fast. Okay, sure. Yeah, that's a trick student told me. They even put in a triple speed, they said. I'm not sure how they can comprehend though, right? It's really hard to talk slower because when I talk fast, it already take me about 10 hours to record, right? So yeah, I better, yeah. Anyway, when you are studying for the tutorial videos, you can feel free to tell me some feedback. Do you think if you think there's anything I should really cover for ANTLR 4, let me know. I can definitely extend by more videos. That's okay. Let me know. Okay, let me just talk about this diagram very quickly. Okay, this is all relevant to your project and assignment 3. Accordingly, since your project is so challenging, I will try to make your assignment number 3 and 4 more relevant to the project itself. It can definitely push you, and also to try to get yourself more familiar with the ANTLR 4. It's quite a cool tool, actually. Very cool. Okay, so now I'll talk very quickly. And at the end of the day, for your particular source language, you have to specify this .g file. It's only a single file. Okay. G4. Ah, good man. You did study the tutorial video. That's good. I agree. G4. And then you use ANTLR 4 to generate it. So now, I would like to maybe hear from you guys to see which. There are two options there for you for ANTLR 4. Either you can go for the more conventional way, where you simply specify all the semantic actions in the same grammar file, or you try the visitor one. Which one do you prefer, just personally?
I don't have a preference here, but I think the visitor
It's more cleaner. It's interesting. As I said in the tutorial video, when I studied the compiler, of course, many years ago, when I first studied that, that's the old version. Yeah, I think if you, for the C compiler, it's called EECS, something like that, yeah. Yeah, exactly. Yeah, yet another compiler, yes, correct. So now, this is the more conventional way. You know what, to be honest with you, I personally still prefer this. That really brings me back about my undergrad life when I was programming this, anyway. Yeah, actually, that's true. Just for you guys' information, you know what my 4080 project was? I did two 4080 when I was, no, not ETF. ETF was done when I was doing my postdoc. That's way more recent. Okay, I'll just mention that to you. It's kind of relevant, right? That's why I'm so much into this kind of a pattern. I think it's valuable. The best way for you to learn about a language is build a tool using its compiler. That's the best way. So that's why I can be more knowledgeable about IFO, right? Imagine that IFO here, IFO doesn't have itself any verification capability. So what I did was my compiler take IFO, my compiler over here, will simply turn that into the input of some tool. The tool name is a bit funny. I'll show it to you. It's called Perfect Developer. Actually, the company is still there. I'll just show it to you just for your interest. The reason that I didn't really include it in the list is that one you have to pay, I guess. Okay. Oh, Perfect Developer. It's a UK company. And the inventor of that actually graduated from Cambridge University, also in theorem proving kind of stuff. Anyway, if you're interested, maybe take a look. Anyway, that's not included in your if you really want to choose this guy here, let me know. Okay. If you really want to choose it, that's fine too. Okay, anyway, that's okay. And I would say during the developments, if you got any trouble with the project, you want to get in touch with me as soon as you can. Okay. Anyway, that's okay. Either this or this, and then the most important bit is about you gotta define your own Java classes in a way that is going to connect the generated classes by ANTLR. Okay, so I wouldn't be too surprised. At the end of the day, you're actually going to get maybe about 20 or 30 classes overall. I wouldn't be surprised. So I would say this is even a bigger project than your 3311, maybe. How many classes did you have for your 3311?
We had some, you gave us for a project something like 30 commands. So that's like one command class for each. And then we have
How about just your model cluster itself?
3 visitors, model, and then one class for each of these models. So that was still like.
Oh yeah, yeah, okay, sure, yeah. Yeah, one thing to mention here.
No, I want my weaknesses for and
Yes, I remember that, yeah. Good, wow. Huh?
When you gave us the type checking, because we used this we had to have one class for each, like an addition, subtraction, something. I was like, I don't remember.
Yeah, I would say, let me mention that. So when we talk about your particular classes, I would say there will be, afterward, this is not a design course, but since you guys took design, and this might be your last semester or your one of the second last semester, you want to do in practice design as much as possible. So I would say when you think about code generation and also think about type checking, you may want to apply the design, so the visitor design pattern. Okay, are you guys okay with that? If you're not, maybe study the iPhone version from my recording. If not, you can also consult with me. But I would say it would be very nice if you can try to visit the pattern here. Okay, and then at the end of the day, your model class will look much more complicated than this, hopefully, right? I'll be very disappointed if you only got a few classes that's so Superman that you don't have decomposition, right? And finally, what I want to mention is, so what I want to mention is, when you study the tutorial video, I would say this is the most fundamental connection to make. So this is the parse tree from ANTLR, okay? And while you are building the parse tree from ANTLR, you want to at the same time build some programming structure, object structure on your own. So that's the most important bit you want to pick up from the tutorial video. That's all I want to say for now. You're going to see the details from the tutorial videos, okay? Okay, any questions? So that's about, take quite a bit of time, right? But I thought it's worthwhile, okay? So now everybody's comfortable, at least to get started with projects, okay? Good. All right, what I will do today, I will finish definitely top-down parsing, and then I haven't really graded your quiz number 2 yet. However, as a makeup for that, I have prepared some exercise for you, which hopefully will help you for quiz number 3 on Wednesday. How about that? Okay. We can do the exercise too. I also got solution printed out for you. Okay, but at least we can try it together quickly. That will give you some idea what you might be asked on Wednesday. But let me go over some slides together with you. Okay, so this is where we actually finish off, roughly speaking, before the reading week. So you should really know about how to calculate the first plus set. Okay, again, that's a definition. I'm going to assume you actually know about it. And then you should also know very well what does it really mean for a grammar to be backtrack free. So that means every pair of the right-hand side alternative for a non-terminal should be, their first plus set should be mutually, should be disjoint, basically. Intersection should be empty. So the exercise we're going to do is going to say, given a grammar, how do you justify whether that's backtrack free or not? If it is not, fix it so that it becomes backtrack free at the end. Okay, that's something we'll do. Okay, this is something I want to just mention very quickly. Okay, that's basically where we stop. Conceptually, you can think about the parsing algorithm you did in assignment number 2. So here, we are just trying to be a little more efficient to avoid backtracking. Every time, if you have the current word to match, you want to check the first plus set for all your production rule. Okay? As an extra exercise for your particular learning, if you can feel free to implement the first and follow sets for your assignments. I know you did already, pretty good. Okay. But it's optional if you want to try. Okay, that's about it. And now I want to talk about some important concept before we make a conclusion about top-down parsing. Can we take a look at this particular grammar here? Okay. Is this backtrack free? Let me remind you quickly, the reason that it would be or would not be backtrack free depends on whether it satisfies the condition we talked about before. Basically, the first plus set for all the right-hand side for a particular non-terminal should be mutually disjoint. They are not. Chelsea.
If you have a factor that has name and you parse a name, let's say that
Mm-hmm.
like, if you detect that it's the square brackets or that, and it's like, oh, this is the wrong one.
Yeah, exactly. Yeah, exactly. That's exactly right. So apparently you can see this grammar here actually is quite obvious because you can see in this case, if I simply got name over here, if I simply got name, what would be the first set for each one of the alternative over here? The name, right? So it's not, in this case, you will see exactly that. So now we actually got, you can see the set over here, they are actually overlapping. So that's not backtrack free. So for example, if I give you the question on Wednesday, give you a grammar, that's how you justify. Okay? Good. And now, this particular problem here is boils down into we have some common prefix for the alternative. You can see the common prefix over here is the name identifier, right? That's a common prefix. And now we want to get rid of it. How do we do it? Basically, there's a technique called left factoring, okay, that we're going to do. It's a very easy technique to actually try, okay? So the problem from the previous grammar really is there's a common prefix name for the multiple right-hand side. So what we really want to do is do something called left factoring to get rid of the common prefix, okay? Basically, let's see this. Just to show you very quickly theoretically, and then we apply that to the example, okay? Thinking this way. Let's say this is a non-terminal. And then the common prefix we have is simply alpha. Okay? And then alpha does not exist in the beginning of gamma 1, gamma 2, and gamma all the j. Okay? That's a general form, which means common prefix only apply to the beta alternative. Okay? So now how do we actually rewrite in such a way that we can get rid of the common prefix? In that case, we'll simply say alpha, and then we introduce a new variable, let's say called b, or a prime. Okay? And then that particular variable is going to produce either beta 1, beta 2, beta n, right? So now we effectively got rid of the common prefix. And then gamma 1, gamma 2, also gamma j, they remain the same. That's just a general pattern. I didn't really write it as an algorithm, but it's just easy to apply. And one thing to warn you about, you may for a particular grammar, you may have to apply the left factoring multiple times. Because whatever resulting grammar you might receive, not this case, but in general, you may have to you may identify more common prefix later, just in general. Okay. So now, how do we convert? Oh, if you look at this particular grammar, which non-terminal should we fix? Factor. Good. And how do we get rid of the common prefix? Okay, why don't we try? Factor produces. Well, basically, we want to factor it out, right? So you can say f prime, right? Oh, sorry. Name, sorry, I forgot that. Name, and then followed by f prime, right? You can think about the name over here is like the alpha, and then this is like a f prime, okay? And what about f prime over here produces epsilon, right? Its name, just that. Epsilon, and then also this particular argument list, and also this particular parameter list. Guys, make sense? Now, question for you. Let's say that's a resulting grammar. Resulting grammar will be f prime, argument list, and more arguments. So now, is it backtrack free? Is it?
Well, don't they share epsilon?
No. When you say they share epsilon, you actually want to see that for every non-terminal. So we can, let's say for this particular non-terminal, what about the first symbol for each one of them? They're simply different, right? So this non-terminal is fine. What about for this one here? That's also fine. There's only one alternative, so you don't even consider it. And now for this guy here, the first symbol is comma, the second one is epsilon. Also, there's no overlapping. Okay? So what Raymond's confusion was, he saw epsilon over here. He also saw epsilon over here, but they belong to different non-terminals, so they don't count. Guys, any question about this? Yes? Oh, you mean here? Oh, I would say the order in which you put this on the paper doesn't really matter. You can put it either at the beginning or the end. However, for assignment number 2, for the algorithm we gave, you may have to put it at the end. I'm not sure if you realize that. Yeah. Anyway, that's fine. Yeah. Okay, so that's about left factoring. Okay. Guys, I have a question for you. So do you want me to, would it be okay if I include left factoring in the quiz number 3, or you rather not? Rather not, okay. That's fine. Since I said it's only up to the previous slide, okay, I'll keep my promise. I'll keep my word. So left factoring is not really in the quiz number 3, but I would say think about, study that together. That will help. Okay, so that's basically this particular exercise over here. And then once we fix it, okay, it'll be okay. So let me just go over a little bit more slides, and then we'll do exercise together. Okay, and I'll leave a little bit more time so you guys can talk about finding partners. Okay. So now, given an arbitrary context-free grammar as input to a top-down parser, basically. So now, number 1 question: how do we avoid a non-terminating parsing process? How do we avoid that? Based on what you have studied. Sure, but what about just non-terminating part? I'm not talking about efficiency. I'm just talking about, I just wanted to at least terminates. Coco. Exactly. No left recursion. Neither direct nor indirect. So you want to convert left recursion to right recursion. So, Ms. Gov, so when I say non-terminating, I'm not talking about efficiency. I just wanted to terminate. For example, in your assignment number 2, right? I didn't say the grammar I give to you will be backtrack free, right? You just do it. So efficiency or not, it's not a concern, okay? Yeah, you didn't have the conversion, exactly. So you gotta assume it's better be like a no left recursion. Okay. Okay, another question here. Oh, how can we minimize the need to backtrack? And now that's really about backtrack free. Look ahead, and also you want to make sure you want to do left factoring, right? So these are the 2 things you want to make sure. Okay, so you can see all the concepts we talk about so far, they're for different purposes. Okay, just review this slide. That's more like a summary for you. And then we'll define LL1. Okay, there'll be a final turn to define, and then we'll do exercise. So now, not every context-free language has a corresponding backtrack-free context-free grammar. It's just a theoretical term, right? Basically, given a particular language you want to really define, you don't really know in general whether it has a backtrack-free, context-free grammar. The textbook says it's an undecidable problem. We don't need to prove it. Okay, you can just assume, just for your knowledge. Okay, so now the following, I'll just make it a little bit more formal. Let's say, if I talk about a particular language, language I, okay, language, sorry, that's L. Okay, that's L, just lowercase l. If I say L is a language I really want to define, okay, whether or not there exists some context-free grammar whose language is L, and then CFG is actually context-free. In general, it's not decidable. There's not an algorithm for that, okay? That's undecidable. However, this is something you should worry about, okay? Given a grammar, whether or not it's context-free, whether or not it's backtrack-free, it is decidable, okay? Now, in that case, I'm just repeating the condition here. Okay, know this condition well. It wouldn't be given to you on Wednesday, okay? Just remember that well. All right. Okay, so now let's mention a little bit more terms and then do a little bit coding, and then we'll do exercise. A recursive-descent parser, okay, there's another term here. Top-down parser, okay? So we'll talk about top-down parsing, right, so far. And then, so now when I say a structure is a set of mutually recursive procedure, I haven't prepared the source code for you, but if you look at the ANTLR generated parser code, that's exactly this kind of recursive-descent parser. Did you get a chance to look at the generated code? Yeah, that's exactly that. Anyway, I'll show everybody maybe on Wednesday when I get prepared, okay? But basically, if you look at the generated code by ANTLR, you will see that the way they implements the parsing algorithm is by, for every non-terminal, they have a corresponding method, basically. And then each method calls itself. That's why it's mutually recursive. Okay, I'll show that to you more example maybe on Wednesday. Okay, each procedure is just one example. Okay, the example I want to give to you is like this. Okay, let's say this. Okay, so we talk about this particular parser is called Recursive-Descent parser. For example, what's generated by ANTLR 4 is a Recursive-Descent parser. By ANTLR 4. Okay, the parser, the parser itself maintains the first plus set for every non-terminal, right? That's also something you can calculate. Let's say we talk about this particular production, expression prime. For this particular variable, we have a corresponding method called expression prime. Okay, for every variable non-terminal, you have a corresponding method in the implementation. Every variable, and similarly, you also for the turn, you also got another method called turn. Okay, like that. And then how does it work? The way it works corresponds to what the first plus set is over here. For example, you can say something like this. If the current word I want to match is either plus or it's minus, it's either plus or minus, it's corresponding to it, right? Either it's matching rule number 2 or rule number 3. In that case, I know that I match the current word, I can go to the next one. And then for the next one, I want to make sure the turn over here can also match, right? If the turn can actually be matched, then I should really go ahead and match the expression prime. If it doesn't match, syntax error, I should return false. Okay? It's a very sketchy implementation. I want to get you some idea. Okay? If you want to see a little more concrete example, the best place to go is to go to generated code by ANTLR 4. Okay? That's the best place to go. And then you can also go for the next one. You can see the next one is about rule number 4. It's either epsilon or it's simply just the closing parenthesis. And then you also got, if they match, you simply return true, and etc. Okay? But this one here, just to show you some code fragment about how you would have implemented the parser manually if you were to. But you don't have to. ANTLR 4 will generate for you exactly this style. It's called Recursive-Descent parser. Okay? And I will show you exactly that on Wednesday. Any question about this? We okay? Okay. All right, let me go back there. And then backtrack free grammar. Okay, it's parser generator. So I didn't say ANTLR 4, but ANTLR 4 is definitely something called parser generator. ANTLR 4 itself is also a parser. Think about ANTLR 4 is also a compiler. Compiler will actually generate a compiler, which can itself also generate a compiler. If you think about the ETF, so now I can bring a little bit more context to some mystery to you. Remember the ETF you did in 3311, right? You try not to. Okay, that's fine. I'll mention that anyway. So let's say ETF dash new, right? And then you put some grammar file over here. Oh yeah, sorry about that. Yeah, thank you. Okay. Remember the ETF program you ran before in 3311? Coco, did you take 3311? When did you take it? But you took a, did they do ETF at that time? Oh yeah, you don't remember. Okay, that's fine. Yeah. Okay, ETF, anyway, you run it, it's going to generate lots of code skeleton. And part of it is actually some parser over there. Yeah, you know what, if you ever wonder about why there's a cluster in the generated ETF code called parse, because that one is itself a parser. Huh? Oh, you did? Tell me what the bug is. You should tell me. Yeah, tell me the other day. Yeah, that one's using some parsing library called Gobo. Anyway, just for your information. Really, there was a bug? Yeah. Let's talk after class. Okay. You should have told me earlier. Yeah. Anyway, that's not important. Okay. And then the parser generator itself should really, the parser itself will keep track of first follow and first plus set, right? And then over here, and it's pretty efficient. Okay, and now LL1 parser. Maybe some of you have heard about this. I think Andres actually asked me about LL1 the other day, but he's not here. But anyway, hopefully he will see this when he listens to the recording. So now people talk about LL1 parser. LL1 is exactly what we have talked about in the last number of lectures. Okay, LL1 stands for, we are basically doing input from left to right. That's the first L. And then we're basically trying to construct a leftmost derivation automatically. That's LL. What about the 1? One label, yeah, one character or one symbol look ahead, right? Exactly. That's LL1. ANTLR4 claimed themselves to be LL star. Just for your information. I didn't mention that in the tutorial. That's a more advanced topic. ANTLR4 claimed themselves to be LL star. I presume, I didn't follow up in more details. I presume what they meant was they're going to do left to right, leftmost derivation, but maybe with an arbitrary number of look-aheads when needed. So they may have some complicated heuristics in their generated parser code. Okay? Anyway, just for your information. But typically, you just say LL1. Okay? And in order to have a grammar that's valid for LL1 parser, it better be backtrack free. Okay, that's how you link all the terms together. Okay, and then, okay, LL1, okay, good. Okay, that's basically what I said, okay? Whenever you talk about LL1 parser, they're expecting something like a backtrack free, okay? Okay, so now what I would like to do is, oh, actually there's something we just talked about already, out the code, okay? Let me see anything else. Okay, so now let's do some exercise, right? We got about 10 minutes. Why don't we do an exercise together? If we finish earlier, we finish earlier. But I think that'll be beneficial for you Wednesday's quiz. What I would do, I got both the question and solution for you. Why don't we do the question first? A solution can pick it up at the end, okay? It might be nice for you to struggle a little bit. Why don't you guys pass around? How about we spend about, let you try maybe for about 3 or 4 minutes, and then we'll do this solution together. I'm going to present the question on the board anyway, if you find it useful. Yeah, let's take about maybe 3 minutes, and then we'll do it together. Just get an idea. Oh, BBC, oh, B is one character. Yeah, B followed by B followed by C. Yeah. Yeah, we got 3 non-terminals only. Yeah. First of all, is it suitable for top-down predictive parser, LL1 parser? Is it? Yes or no? No. Good. Okay. Carry on. Okay. Yeah. It's not really working for me. Okay, write it down. Yeah, I might just interrupt you quickly. So if you're given this kind of question, I would say either you decide it is suitable. In that case, you want to make sure, you want to show to me it satisfies the LL1 condition. If it does not satisfy, you want to correct the problem and show it, the fix actually make it LL1 compatible. Okay, that's kind of the, you will see the detailed solution at the end. So guys, very quick check together with you. What is the reason you don't think this is suitable for LL1? Yes, there are 2 things over here, basically, right? Basically, one is you got some left recursion. Okay, very quickly, just for those of you who have not been able to identify. This is a common prefix, right? So that's one part. because in that case, the first plus set for the two alternatives will be overlapping. And also, you can see left recursion. Okay? Let me remind you, in this particular example, you wouldn't see that. But when I give you left recursion, it may be direct, like this case, or it might be indirect. For example, R goes to A goes to B, and B go back to R. Be careful with that. But it's not in this example, right? So which one you want to get rid of first? It doesn't matter. What about we say the left recursion? We can get rid of that first. Doesn't matter. Yeah. Okay, I'll give you maybe one or two more minutes, and then we'll do it together, right? And then the detailed justification as to why it would be LL1, keep it in the solution. But I'll give you some idea how you should organize your answer. Okay, shall we solve it together? Just in case, just to save time. How can we remove this left recursion? Yes, that's common prefix. Okay, be careful. Okay. Yeah, exactly. Right? You would say basically R produces R prime, and then?
And then the rest of its rules as well, like ABA, CABA. That's how I have it. And then R prime produces ABA, CABA.
Okay, R prime would be R prime followed by BC. Actually, you know what? It goes like this, okay? You gotta review maybe the algorithm yourself quickly. Exactly. BC and then R prime. Or it can be epsilon, right? Okay, just remember. And then you can also say, oh, sorry, this should be R prime. And then the R itself will actually go to the rest. Either this guy here or this guy here, right? You'll be ABA followed by R prime, or also CABA followed by R prime. Convince yourself this is working, okay? Yeah, so this might dates back to maybe about a few lectures ago, but you want to make sure you can do that, okay? You'll see the solution later. Okay, this one here, although not to be in the quiz on Wednesday, but just do it anyway, okay? This one will be very easy. So now I can say Q now produces, why don't I simply say maybe just Q prime? BQ, yes, yes. B, Q prime. How about Q prime? Okay. And then Q prime would be BC or C, right? That one's also easy, okay? So now, guys, question for you, right? What I got at the end. This production rule, the blue one seems to be fine. This orange one that I just fixed seems to be fine too. And this green one also seems to be fine. However, how do you justify by saying the blue, the orange, and the green all together, they are LL1 says compatible? Question. Exactly. That's what you got to do. Okay. What you got to do is basically, I would say the best way to present, you will see in the solution, so you will know what to expect. The best way to present is goes like this. Of course, if you don't have to follow, I'm just saying it's the best from my point of view. You may want to show for every non-terminal, let's say for L here, and then you also show for R here. Also, you show for R prime. So L, R, R prime, and also Q and Q prime, okay? Q and, to running out of space, sorry. And also you got Q prime over here. And first of all, you don't have to worry about Q because that one only has a single alternative, right? You don't have to worry about overlapping. What you gotta do is, for every one of them, think about the alternative that you have to. So think about alternative. And for example, let's say for L. L would be RA, okay? And also QBA. And then what would be the first plus set? In that case, fill it in. And now You want to know what the intersection is. You will hope the intersection is simply just an empty set. So that's kind of the layout. That'll be very clear. Okay, any questions about this exercise? Chelsea, quickly.
Just to verify, you had that, like that logic statement that said that like for every rule.
Yes, for the LL1 condition, backtrack free. Yeah.
For it to be backtrack free, first set for every production in every rule happens that way.
Yes, you wanna say it goes like this. For every non-terminals production, you want to make sure for that particular non-terminal, every alternative got non-overlapping first plus sets. Okay, guys, any questions? Okay, so I'll finish now, and then make sure you pick up your solution over here. Okay.